Hey everybody, so we are going to now begin our dive into chapter 13, which is going to be an introductory chapter on vector functions. So I will go ahead and warn everybody, so if you are going on to Calculus 4 next semester after this class, this chapter is going to help build the foundation to what they expect you to already know when you get into that class, because when you get to multivariable calculus, it's all in vector notation, so that is what you're going to have to work with. So make sure you pay close attention over the next 4 sections we cover so you can understand the basics and stuff that you're expected to know. All right, so let's talk about what a vector function is just from the get-go. So definition is a vector valued function, or just simply a vector function, is simply any function that maps a set of real numbers to a set of vectors. We will primarily work with vector functions in 3 dimensions, but hypothetically you could work in any dimensions here, even in 2D. There's a couple different ways that you can denote this. Since these are vector functions, you will need to be able to write everything as, we're going to call it the vector R. So R of t is a vector, can either be written in component form, which I prefer, or if you prefer IJK form, that is perfectly fine as well. What you will notice though in this chapter is that unlike the last chapter where most of those components for IJK were numbers, we now need to let these actually be functions of t, because our ultimate goal is we're going to relate a lot of this stuff to parametric equations like we did back in chapter 10. So the f, the g, and the h functions are just any real valued component functions that you have seen. Natural logs, exponentials, trig, algebraic. You're going to see it all throughout this chapter 13. So what can we do with these functions? Well, this is where we're going to start introducing some of the calculus concepts that you've learned throughout Cal 1 and 2 and how they apply to vector functions. So go back to Cal 1 for a second. First thing you learn calculus-wise, what is limits? How do you apply a limit of a vector valued function? So if we define a vector function R of t as being any 3 components of a function, then when you take the limit as t approaches a of that vector function, you're really going to end up doing 3 problems in one. You must apply the limit as t approaches a of all 3 parts. Now, each part may give you a different answer. Each part may be a completely different technique. For example, you may be able to just plug the number in and you may be done. Or you may have to do L'Hopital's rule. Or you may have to do some kind of other cleverness that you've learned throughout Cal 1 and even some in Cal 2. So we're going to look at an example in a second, but anything is fair game as far as the limit rules you have learned before. Now, the big thing you're going to see me say a lot over the next few sections is that when you're doing calculus, most of these calculus techniques are completely dependent on as long as the calculus property can be applied to every single part of the vector. So with limits, this limit is only going to exist if 3 parts exist. If any of these 3 give you an answer of d and e, then the overall limit of this vector function will be d and e. So it's either all or nothing in these cases. So let's look at an example of where you could use this, just kind of showing you how it applies. So here's an example. I want you to find the limit as t approaches 0 of the following vector function. Your I component is e to the negative 3t. J component is t squared over sine squared t, and your k component is the double angle of cosine. So while you may be able to do this all at one time in your head, remember on your test you got to be able to show me steps. So what I usually do with all these vector ideas is I'm going to break it down one by one. I'm going to begin by doing the limit as t approaches 0 of the I component, which is just e to the negative 3t. Now in this case, you can just plug the t equals 0 in, get e to the 0, which is 1. So in your final answer, when I start to rewrite this, when your 1 being your I component, you just get an I. You just stick the coefficient in front of the component that you're working with. Continuing on, you can then do the limit as t approaches 0 of t squared over sine squared t. But you'll remember, if you plug 0 into this, you run into a very, very popular fraction in limits, and that is 0 over 0. Now, we've learned in previous classes that we can apply L'Hopital's rule to get our answer. So let's remember what L'Hopital's rule says. It says that you can leave the limit exactly as it is. You can apply the derivative of the top and bottom separately. So the derivative of t squared is 2t. Sine squared is going to be a chain rule, so it's going to be 2 sine t cosine t. Unfortunately, though, is that when you plug 0 into this, you're going to end up actually getting 0 over 0 again. Now, you could take L'Hopital's rule again, but before you do that, let's do some simplifying, because usually if you can simplify along the way, maybe it comes out a little bit nicer. And I know what you're thinking. Oh, the 2's cancel. That's not actually what I would do here. I'm not going to actually touch the 2t on top, because what I recognize is at the bottom is an identity that you learned in trig. That is exactly the double angle of sine. Now, while you're still going to get 0 over 0 as an answer, you can now do L'Hopital's rule a little bit easier than maybe the product rule would have been earlier. Now, product rule is not wrong. You just may get to be a little bit more careful. But taking the derivative of this, you should get a 2 on top, and sine 2t becomes 2 cosine of 2t. Plugging 0 into that, if you want to cancel the 2's now, you can, but I'll just leave them alone. This would be 2 over 2 times, and the cosine of 0 is 1. Simplifying that, you get 1 as well. Just a nice little coincidence there. But in your final answer, that essentially means you now have a plus j component. And last but not least, you're now going to do the limit as t approaches 0 of the double angle of cosine. If you plug 0 into that, you just get the cosine of 0, which is 1. So very nice coincidence here that all 3 components were 1s. So there's 2 ways you can write this. You can either leave it in ijk form and your answer is I plus j plus k, or if you're like me, I prefer component form. So your answer would be 1, 1, 1. WebAssign will accept either one, I believe, and on a test, especially the final exam, I would accept either one as well. So this is your limit. And any limit vector function can be done the same way, so I'm not going to do any more of these, but just apply the rules of limits that you've learned from previous classes. What we're going to spend the rest of this section really talking about is more of the graphs of vector functions. Now, I'm not going to make you graph a lot of this stuff, but there are some basic things that I do want to cover and make sure that you have a good understanding of what's happening. So let's first suppose that we have the 3 functions, f, g, and h are all continuous real-valued functions on a certain interval I. Then what we can do is we can take the set C of all points in those functions in space, and this is called a space curve. It's kind of a cool name, aka you can also call this a 3D curve. But these are types of things that can be generated from 3 different kinds of functions. Some of these can be very pretty. Some of them can be very, very ugly. It depends on what kind of functions you want to work with. Now, while there are many different names to these space curves, one of the ones I want to look at first is actually called the helix. So a special space curve that we talk about is a helix, and that is a curve that spirals upward around a cylinder. So over here on the right, let's focus on this one, then I'll come back to the left graph in a second. So if you look at this helix over here, so this is our helix, you see that it is a graph that starts at the point 1, 0, 0, starts making a spiral, it would cross at the point 0, 1, pi over 2, and it continues this trend on the way up. So what I want to talk about here is something we'll have to do a little bit later. Could you figure out what vector function this actually is? Now we're going to kind of assume that this is going to be our t equals 0 spot, and that's going to be kind of it, and then I have to kind of pause there before I give you any more numbers. So remember, when it comes to a vector function, you need 3 parts. There needs to be an x component, a y component, and a z component. And one of the challenges is building the relationship between the 3 numbers and noticing the pattern. So think about it for a second. See if you can figure out a pattern of where these numbers are dependent on one another. Remember, they can be any function you can think of. Figure it out. Give you a few more seconds. If you need to pause the video to think a little longer, that's fine. All right, so here's what I notice here is that when you look at this 0 right here, look at the z component. If I let that be my t value, because that number, I notice there's an angle coming up in a minute, so I'm going to call that my t. What trig function would give you the values of x and y? Well, what of 0 would give you 1? Well, if I think about it for a second from trig, that's cosine t. And then what of 0 gives you 0? Well, there's actually a couple different ones. I'm going to go with the basic one. Let's do sine of t. And then we're going to verify that that is correct for the next point. So if I let the angle be pi over 2, what's cosine pi over 2? It's 0. And what's sine of pi over 2? it is 1. And this would continue because as this angle rises, the values of your points do not change. Because while these are going to go back and forth, the z value is making the number go higher and therefore creating the helix. So this helix right here is actually being generated by the following vector function. Now, that is a very, very special case. Most of the time in real-world applications, your vector functions look something like this, where you have some ugly contour graph, and that every point, it could do all kinds of loops, but the big thing is you'll notice, just like when we did parametric graphs back in chapter 10, you need to use arrows to indicate the direction in which the vector curve is traveling. And I'll do that a lot when we're drawing graphs over the next few lessons. But that kind of gives you an idea of what we're going to do for the rest of this section. So let's do an example then. We'll start in 2D and then I'll do a 3D example for you. I want you to sketch this curve with the given vector equation and then indicate with an arrow the direction in which t moves. So what do we know about this? We know that the vector function is defined as r of t equals sine t and t. And I said a few minutes ago, remember that we're going to try to relate this to a parametric equation. So in this case, if I let x equals sine of t, and I let y equal t, what relationship could you build to maybe graph a curve? Because remember, I want you to sketch this curve. Now it's a 2D vector, so we're just going to have a 2D graph over here. Any ideas? If you need to pause the video, think about it, that's fine before I give you the answer. So there's two ways to think about this. First thing you should notice is that if since t is y, couldn't you just substitute that directly in? We could say that x is equivalent to the sine of y. That is a curve that we could draw. But what about the other way? What if you want to get t by itself? Remember, kind of like eliminating the parameter back in chapter 10. In the x equation, if you get t by itself and plug it in, you could say that y is the inverse sine of x. These are actually the exact same curve. Now the question is, which one of these would you rather draw? If you know what an inverse sine graph looks like, then you can just generate it on the graph and do it with arrows. I typically stick with the first one. I'm going to go with this one over here. Now be careful because it is defined as x equals sine of y. So the angles you have to use are your y values. So let's say 0, pi over 2, pi, 3 pi over 2, and 2 pi. You're going to plug these y values in to generate x's. So sine of 0 is 0, sine of pi over 2 is 1, and then we'll continue this throughout. And then you're going to plot these points in order because you need to know the direction in which the curve is moving. So I would start at 0, 0, then I would go to 1, we'll just call this pi over 2. Then I'm going to go to 0 pi, so all these little marks are increments of pi over 2's. Then you're going to go to -1, 3 pi over 2. And then finally 0, 2 pi. And when you draw your curve, you could draw it a little bit further both directions, but essentially you'll notice that this creates a sine curve, but going in the y direction and not in the x direction that you're used to. So these two functions right here is this curve. So this would be an example of the curve or the space curve sine t, t in a two-dimensional space. So it's being able to take your original function, relate it to x and y, and then figure out what is a curve that you have seen before or could generate yourself using prior knowledge. All right, what about 3D space? Now 3D is where it can get a little tricky, so let's start with a very easy one to get you started. Same instructions. Sketch the curve with the given vector equation. Indicate with an arrow the direction in which t is moving. This one is t, 2 minus t, and 2t. And I'm going to start it off very, very similar as I did the last one. I'm going to try to relate this into a parametric curve. So I could say that x equals t, y equals 2 minus t, and z equals 2t. Now look at that. Is that something maybe we've seen before? So think about it. If you need to pause the video, do that again. Think about what that is. Got it? Well, hopefully some of y'all have recognized from a couple sections ago that this is the equation of a parametric line. All three of those functions are linear functions, and put together in three terms makes it a 3D line. So we need to now know how do you draw this 3D line? So here we go. We're going to draw our 3D parameters, x, y, and z. Think about what you're being asked here. All right, so how do you draw this line? Well, I know I could find the direction vector because I know what direction it's going. Remember, that's the coefficients of your t's. That would be 1, -1, 2. But the other thing you need is, what else do we need for lines? A point? You got to find some point. And it doesn't matter which one you is. Just pick a t value. I'm going to make it easy. I'm going to let t be 0. That's going to be one of the points on this line. So plugging 0 in would give me 0, 2, 0. So kind of like when you graph lines in 2 dimensions, plot that point first. I'm going to go 2 units in the y direction. And then kind of like slope, but it's not called slope, you're going to draw the direction from the point you plotted. So I'm going to go 1 unit in the x, -1 in the y, and 2 units in the z. So back 1, over 1, and up 2. And it's going to be somewhere about right there. Now, technically, this line does go on forever. Remember that, because remember, I just picked these arbitrary points. Make sure, though, that since we went from this point first to this point second, that is indicating that's why my arrow is going in that direction. So that is how you would define a vector function of a line into a parametric equation of a line, and this is how you would sketch those 3D lines. All right, so here's where it gets tricky. What if you have a non-linear 3D graph you have to draw? So what about x equals t cosine t, y equals t, and z equals t sine t, where I need to restrict t being greater than or equal to 0? First thing you will notice is that these are not linear functions. So this is not going to be a straight line. We've got to find another way to relate all 3 of these equations, because I went ahead and wrote it in parametric form for you to save a little bit of time. So let's think about how we could relate these. The x and the z are a little bit more complicated. The y, a little bit nicer. Is there a way that we can put all these together using some kind of algebraic operations? Now, if you want to try to figure this out yourself, think about adding, subtracting, using different properties of PEMDAS. That's kind of my suggestion. Can you use things in PEMDAS to relate all 3 of these together? All right, so like I said, I do suggest everybody take a pause for a second and try to figure it out, because this is the type of critical thinking you will have to do. So after you've done thinking, unpause the video and you can kind of see what the idea comes from. All right, well, welcome back if you took a pause. So let's talk about how you can relate these three equations together. So notice this. I see a cosine and a sine that have a t attached to them, but the y only has a t. My thought process is, how do I get rid of cosine and sine and make it maybe a coefficient? What if we did this? What if I take the x term and the z term, square them, and add them together? Because what that's going to do is going to allow you to try to develop an identity involved so that these trig functions will go away. So let's see what happens. This is t cosine t squared plus t sine of t squared, which does simplify into t squared cosine squared t plus t squared sine squared t. You can factor the t squared out of both of those. And you'll notice that was the idea. Now, this is an identity. That's just going to go to 1, and you have t squared. But what is t squared? At the top, the easy equation, y is t. So if y is t, then what's t squared got to be? It's got to be y squared. Now, all that stuff comes from me doing the 2 operations of exponents and addition. So we have now created the equation that x squared plus z squared is y squared. This is the equation of the graph I need to draw. This is why we spent about 20 or 30 minutes going over the last section. In 12.6, that is one of your quadratic surfaces on the chart that I asked you to learn. So if you look back, this is an example of a 3-dimensional cone. Now you're going to have to draw this a little bit differently than we did in the last section, because I don't remember this cone is now coming from a vector function, not from the original. This is not the original. This is just a rendition of the vector function. So when I see this, what do we remember about the cone? Well, the cone has an isolated term, y squared. So that means that the cone should only go on the y-axis. But also, since my t values are restricted to being positive, you only need to go in the positive y direction in this case. There should be no negative values, so we're going to stay going towards the y value. All right, so now don't just draw a cone. Here's kind of what I do. I know, I'm going to use little dotted lines for reference. I know the cone needs to go in that direction, but it's got to be a vector function type of line. But it's going to probably be some kind of curve. So let's see. I believe if we kind of start spiraling, kind of like the helix a little bit earlier, because remember cosine and sine were involved with that. But since this has got extra variables involved, your width keeps getting larger and larger to eventually you develop a three-dimensional cone as a space curve. So while this function looks very, very ugly, you're able to use order of operations, kind of using those ideas. You're able to simplify it down into a very nice equation that you've seen before, and then you relate it by drawing it as a space curve. So that is what this curve does look like. All right, how about intersections? So there's a couple different ways intersections can work in vector functions. The first one's a really, really direct one where it's pretty much right there in front of you and we can just go for it. So let's talk about that. Can we find at what points does the following vector function, ti plus 2t minus t squared k, where does this intersect the paraboloid that we covered back in section 12.6? This is where it comes back to me harping about parametric equations. In vector curves, we can take those functions, not y, and relate them as a parametric. Since the first term is I, we can call that x, and this is k. You saw I almost messed up, so don't make a boo-boo. This is k, so that's going to be your z. We can directly substitute these into our paraboloid equation, and then it becomes an algebra problem. So in this case, z is 2t minus t squared equals you square x, which is t squared, and since there is no y component of this vector function, we just skip over that part. Do a little arithmetic. It may make sense to add t squared to both sides, but that's not how you solve this. Remember in algebra, when you have a quadratic, you have to get the term equal to 0. So I'm going to subtract the t squared over and make it 2t minus 2t squared equals 0, because now I can factor out the greatest common factor and make it 2t times 1 minus t equals 0. Set both of those equal to 0, and you'll have t equals 0 and t equals 1. But remember, those are not points. You now must take those. You have an x and a z. The y is going to always be 0 based on this vector function, but x and z are dependent on what t values you get. So in this case, if I focus on t equals 0, plug that into the x and z. You'll get 0 for x. We know y is 0, and 0 minus 0 is also 0. So that means that these two curves actually intersect at the origin. And then for t equals 1, if you plug them in, you'll get an x value of 1. Y is still going to be 0, and then 2 minus 1 is 1. These are your intersection points. Now, as me being a visual learner and a visual teacher, that may not make sense. Okay, why does it cross twice? So even though this is not part of the problem, I think this will help kind of make the understanding a little bit better about what's happening. So let me draw these graphs real quick. X, Y, Z. Now from the last section in 12.6, this paraboloid is going to be on the z-axis because that is the isolated linear term. So it looks, once again, kind of a rough sketch here. It looks something like this. That is your paraboloid. You have 2 points. One of these is at the origin, so we'll put a big dot right there. And then going to the point 1, 0, 1, so that's 1 unit this way and 1 unit up, that's going to be somewhere over here. Now the t parameters do give us an order in which they intersect. Now this graph is not drawn to scale, but if I had to guess, I bet your graph approaches from the bottom, enters inside of the paraboloid, so I'll use a dotted line there, and then exits out of the paraboloid at a different spot. It probably looks something like a parabola as well because one of your components is a quadratic function. Now the arrow's got to be tacked on, but that's kind of a rough sketch of what's happening here. Now that's not maybe 100% accurate, but it kind of gives you an idea of why are these crossing twice and why does it cross down here first versus up here second. So that's how you can figure out where a vector function and a quadratic surface intersect each other. All right, and last but not least, this is where I mentioned in class before we left for spring break that there are times that there could be multiple correct answers, and this is an example of that. Can we find any vector function that represents the curve of intersection of these two surfaces? So we have the cylinder that we saw in the last section, and then just a general surface that we're going to define as z equals x times y. When you look at both of these, you will notice that you will not be able to find z unless you know what x and y are. But that's okay. We have an equation that is solely based on x and y. You've now got to think of what functions of t, and you cannot use constants here. It's got to be a function of t. Can you give me an x and a y function of t without constants that if you plugged in will give you 4? Once again, if you want to pause the video, I do highly encourage that because that's going to help this out. But think about what x and y can be, and after you have a few guesses or your idea, unpause the video and see if you get what I get. All right, welcome back. So if you thought about this and you did not use constants, so don't use something like 2, 0 or 0, 2. It's not what we want to do. And don't do root 2 and root 2. I want to see if you can do this. What's squared and added together will create a constant? Well, if you think back to trig, we did this one a little bit earlier today. You've hopefully all remember that sine squared plus cosine squared is 1. But I need this to equal 4. So what coefficient could I add in front? Well, the answer is a 2. Because if I add, oops, sorry, let me erase that real quick. Let me mark it off just faster. If I were to write this as 2 sine t squared plus 2 cosine t squared, if you were to work this out, it would end up evaluating into 4 because you would square both terms. That would give you 4 sine squared plus 4 cosine squared, and that simplifies into the value of 4. That means you have an x value and you have a y. If you worked it out and flip-flop these two, that's fine. It's the same answer in the long run, but whichever way you did it, you can now plug this x and y into this equation, and you're able to evaluate what z is. So z is going to end up equaling 2 sine t times 2 cosine t, which does simplify into 4 sine t cosine t, which is the same thing. And once again, I'm using identities here because that's the most simplified way of doing this. That is the same thing as 2 times 2 sine t cosine t, which is the same thing as 2 times the double angle of sine. This is your identity right here. Then you put it all together because it wants you to find the vector function. So I can say that r of t is going to be defined as, in my case, 2 sine t for x, 2 cosine t, sorry, bad handwriting, 2 cosine t for y, and 2 times the double angle of sine for z. This vector function represents the intersection of the cylinder and the surface in this case. That is the end of section 13.1. In the next video, we will introduce derivatives and integration because now we got to learn how to take a derivative and how to integrate vector functions. But the good news is it's very similar to the limits we covered earlier in this section. See y'all all in section 13.2.